a crash course on zero-knowledge proof. Today's topic is still some basic concepts, including finite fields, commitment, and also a minimal zero-knowledge proof called Schnorr identification protocol. Hello, wait, hello. Does that work? Hello, yeah. Okay, the first topic is about finite field. Okay, it is an algebraic concept which could be complicated. But still we can use them as black boxes. Basically, there are two. Sorry, I think. Okay, we have two types of finite fields, basically. So the first type is like FP, so it's called a prime field. So P is a prime number. So it's a prime number. Or the finite fields like P to K, and the K is the power of a prime number. So it's called extension field. Extension field. Okay, extension field can be treated as a vector of prime field. So it turns out, all finite fields. So finite means the one finite fields which is a set with finite number of elements. So either the number of elements is prime, or it's a power of prime.
Okay.
Oh, I think okay. Okay, here I'll give you an example. For example, 7 is a prime number, okay. This doesn't work. Sorry?
Do you want to try?
Yeah, I think. Yeah, okay. Thank you. So F7 is a set with 7 elements from 0, 1, 2, 3, 4, 5, 6. It's a F7, okay? F7 is like from 0 all the way to 6. So why finite field? Because we want a set of numbers where the addition, multiplication, division, and subtraction, the operation of any two elements from this field can be, closed. So basically, so let's define what plus is like. Okay, when A plus B, so we define the addition as A plus B mod 7, mod 7, mod 7. And A times B, we define it as A times B mod 7. Okay. Now we define a plus and a multiplication, and a mode is the prime number. So why prime number? Because if the modulus is a prime, then basically we can define the A divide B as A times B, the inverse, and basically every element except 0 has its own inverse element. So we can define every inverse element for every element except 0. Okay. For example, 1 minus the inverse of 1 is 1. Okay. Yes. 1 like and it's 4, right? Sorry. Right. Why? Because 2 times 4 equals to 8, and 8 mod 7 equals 1. So, okay. So the inverse of 2 equals to 4. So every inverse of the element is still in the set except 0. So 0, we cannot divide by 0. So, okay. In mathematical terminology, so the F7 is an additive group. Okay. Is F7 remove 0 is a multiplicative group. So group means, okay, the option of set is closed. We just add or multiply two elements from the group, then the result is still in the group. But remember that for a group we have only one binary operator. So okay, it's a mess, but we just skip this detail. We use that at a black box. It's gonna be okay for our minimal example. So so anyone can answer that what the inverse of 3 still in the set except 0. So anyone can answer this. What's the inverse of 3? So inverse means that 3, okay, some number x times, sorry, 3 times inverse of 3 equals to 1. Okay. Cool. Anyone can give me the answer, the quick question. Sorry, 5? Okay, right. Because we can do a quick verification, and 5 times 3 equals to 15, and mod 7 equals 1, yes. Basically, we can do more exact, but here we just, okay. It's a finite field, it's a prime field, but in practical, we need the P is sufficiently large. Probably for example, 256 bit long. So P is very big. Then we got some the security property. But another very good property of F7 or any prime field is like its multiplicative group is like a cyclic group. Okay, cyclic group. That means that we can find some. Okay, among those elements, there's some special element which can be used as a generator. Means that we can use that one number to generate all other elements except 0. Okay, let me try. Okay. So let's take 2. Okay, 2 is a element, right, in the F7. So 2 generates 2, right? And then we'll use the multiplication. So 2 times 2 equals 4. Means that we can use 2 to generate 4, right? Now because we got 4, now we have 2 and 4, then we time 2, 4. Then we got 1, right? Because 2 times 4 equals to 8, and mode 7 is 1. So now we get 2, 4, 1. Oh, and the next, right? Next, we time 2, 1 still equals to 2. Okay. Then we got the infinite loop, right? By using 2, we only generate 2, 4, 1. Okay, then 2 is not a generator. It's not a generator. But, okay, the fact is, okay, this group is cyclic. It means that it must have some element as generator. Okay, let's try another element like 3. Okay, 3 generates itself, and 3 times 3 equals to 2, right? Now we generate from 3, we got 2. Then let's continue. 3 times 2 equals to 6, right? And 6 times 3, we got 4, right? And 3 times 4, okay, 5. And 3 times 5, okay, because 5 is the inverse of 3, and then we got 1. All right. Here we can see that we use 3. We can generate all the elements except 0 of the 7. So now we can say that the F7 cross can be written as this. Is we use a angle bracket to with 3 inside, means that okay, this group can be generated by 3. Okay, so the generator. Okay, maybe here I can give you a homework. You can find another generator in this group, in this set. Okay. But right now, okay. Okay. Then, if the P is very large, for example, P like 256 bits long, then we give a we find, for example, find any generator from FP as a generator. So it means that FP cross equal to the G, right? The angle bracket is G. Means that G can generate all the elements from FP except 0. For example, there's a G to A equal to some B, right? If G is public, is a parameter of our scheme, our protocol, then B equals to log G A, right? Sorry. Yeah. A is B, right? Basically, we should do a logarithm operation to, if anybody get a B, then the problem is that how can we get an A? So, but it turns out, okay, this computation is very hard. It's so-called discrete log. Discrete log problem. If the P, here I think the P probably or even larger. Okay, here P is 256. It's not secure at all. Sorry, P has to be very large. I think still not large. I'm not quite sure about the current state of art, the attack. I think probably P should be very, very large. Then we compute the log. It's very hard. So first of all, we have a very large prime. Then we choose some element as the generator, G from P. Then basically we can hide a value. For example, A. G to A. We can hide G to compute a new number, G to A. Then basically we can send G to A to anybody. So we just assume, okay, that guy hasn't any powerful computer like a quantum computer. So basically that guy cannot get A. So this is very powerful right now. So, but it won't be safe probably 10 years or 20 years after. So if quantum computer become very practical, the common. Okay, but right now, so many cryptographic construction based on discrete log problem. Sometimes in crypto, we use another variant called elliptic curve discrete log problem. So we don't use that P straightforward. We use elliptic curve. I think today is another talk about introduction to elliptic curve. So I won't see too much here right now. Okay, so far, any question about finite field? Any question? Okay. 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 Let's move on to this. Then we can use the G2A this form to construct a very useful cryptographic tool called commitment. So commitment. A commitment is like a computation over a piece of data. Then we get a short representation of that data. The commitment can be very small, for example, the data can be very large, and also the hash sometimes can be used as a commitment, but basically we have other commitment implementations besides hash. For example, here we use the discrete log problem. Based on that, we build a commitment scheme. So can commit. Okay, for simplicity, here we only commit one value, like v, and use some, the generator from a sufficient large prime number, prime field, equals to g to v. So here we got this. Okay, it's a commitment operation. Then for the commitment, it's a cryptographic tool. Then we'll have to prove something about the commitment. Basically, it has two very important properties. The first one called the hiding. Hiding means like if we got the G to V, it's very difficult, or we assume it's possible to get V. Okay. So if we put V to the power of G, then basically it's hidden. Okay. The second property is called binding. Binding means like if another V prime is not equal to V, then the GV is not equal to GV prime. Or it's computationally hard to generate another commitment which they are equal, which is each other. That means that, okay, the one commitment is corresponding to a unique data file. Basically, it's not actually impossible, but it's very, okay, or we can say it's a computational impossible to get one commitment, but that commitment is corresponding to two different data file or data pieces. Okay. The hiding, okay, hiding is okay. We can basically put a useful data or privacy into, okay, means imagine that commitment as a box. We'll put the data into the box and log it up, and then we can basically send the box to anywhere, even put it on chain. Okay, currently, many modern stacks or even other cryptographic protocols, they rely heavily on this construction. But here, as I mentioned, that because currently the quantum computer is coming, so I have to do something to hide our privacy, to protect our privacy even after the computer is practical. So this is the next very important concept called Peterson commitment. Peterson commitment. So, okay. Okay, Peterson commitment. Peterson commitment is saying that, okay, we need two generators, and a G and an H from a very large prime field. Okay, remember that G and H, they are not equal. And then when we commit to a value V with G and H equals to G to V and times H to R. And here R is kind of a random number. Okay, random. Okay, yes. So we commit a value V. We append the commitment of V with another random number. Sometimes it's called blind factor, blending factor or blending, blender or something, blending factor, almost same. To protect the commitment. Okay. Here's a question. So, what are differences between a commit V like this way and a commit V like this way? So, what are differences? So, if you are a developer, you want to use commitment to improve your application, that basically right now you have two options. So, use this one, pretty straightforward. And here you have to ask, the random number generator to get additional random number to protect your privacy. So, okay. So any thought or any idea or any answer? So basically, we have two options here. Yeah.
You get a more complex equation using Peterson?
Sorry. Yeah.
You get a more complex equation or polynomial using Peterson commitment?
I don't understand. Say it again.
So the question is, which one is the difference between a simple commitment and Peterson commitment?
Yeah.
In my understanding is that you get a more complex polynomial.
More complex polynomial. Okay.
When you use Peterson commitments.
Okay, probably from some point of view. Yeah.
Yeah, I think obviously it would be, it's complex to derive all the numbers that you are using. It's harder to derive the generator that you are using for the second equation.
Okay.
And also, but I don't know how expensive it is computationally to generate that commitment. Work on that.
Okay, good. Yeah. The second approach means that the people who want to commit V should do more computation, right? Because there are two exponential operations. So, but here is I think the first difference between the two commit schemes that when we commit V the second time, basically the prover or committer can choose a different random number to generate different commitments. So, but here the commitment scheme it's a one-to-one map, right? So we have when V is a one-to-one map to G to V, right? But here we have V. We use different random number or map to basically different R prime. So if we choose different blending factor, basically we generate a different commitment. But two different commitments according to the same private data, right? So that's why Peterson commitment is more useful. It's because if you want to get the better ZK property, then we should use Peterson's commitment. I think by default, we should use Peterson commitment because For example, if in your application you commit V many times, multiple times, then the verifier or anybody doing eavesdropping, something like that, then they can derive that, okay, the 2 times you commit the same data, even the attacker cannot know what value of the V is, but the attacker will know, okay, the two commitments actually correspond to one value. But if we use a different dependent commitment, then for each time when we commit our privacy, we use a different blending factor. The attacker or someone doing eavesdropping cannot derive he or she cannot know that, okay, they basically you commit the same data, okay. Then I think tomorrow we will prove this intuition formally. But today we just get the intuition, okay. The Peterson commitment satisfy such property we call it the perfect hiding. Perfect hiding. The perfect hiding. Imagine after 100 years, right? If we put right now, we put G2V times H2R on chain, put it on chain. Then after 100 years, the quantum computer will be common, and someone will using quantum computer to compute, right? The attacker will get something. The attacker cannot compute the V, even using quantum computer. Why? Because here we do some simple calculation, right? So as I said, G and H both from FP. Then, and both of them are generators, right? So that says that H can also be generated by G, right? So basically, we assume that H equals to G to, for example, lambda. Lambda is a number. We can use G to generate H, right? G to lambda equals to H, right? If we commit value, use a blending factor as R, then we got the commitment. Let's use a square bracket as commitment equals to GV times HR equals to GV times G lambda R equals to V plus G2V plus lambda times R. Okay. Basically, we'll put on chain is this value, right? Is this value. Put it on chain. And in the future, 100 years ago, some guy, okay, assume he can efficiently compute the discrete log problem. Then the V plus lambda times R will be extracted, right? But if the attacker don't know what R is, the attacker won't know what the V is, right? So if we keep secret both on the privacy V and also the blending factor R, then okay, we'll be safe, right? We'll be safe even after the quantum computer. Okay, this is what I call the perfect hiding. It means like no matter what powerful the attacker is, the attacker cannot know the hidden value. Okay. Okay, so far Any question about this? Any question? Okay. You this one?
Yes, this one are used as nullifier or is a basis for nullifiers?
Nullifier?
Yes, like
Okay.
if you have the
Yeah, sometimes it's related to nullifier in anonymous coin. Like, yeah, yes, similar, but this is more primitive.
okay.
Yeah. Yeah. Okay.
Can you use a simple commitment or a Pearson commitment whenever you want? Like, if I choose to do this, like if model complexity isn't a problem, like for instance,
Sorry, what?
if model complexity isn't a problem.
Model complexity. I mean,
Yes, for instance, what if I have all the computational power in the world, for instance?
okay.
Then is there any situation where I would like to use it would be better to use a simple commitment?
It depends. It depends. Yeah, yeah. So,
The computational power or efficiency?
because the protocol, okay, commitment is okay. The commitment is the very primitive operation for any practical protocol. So, if you want to do something like a ZKML protocol, the protocol maybe they're large. So commitment. So which commitment scheme you want to choose? It depends on the protocol design. So it's hard to say. Okay, which one is better? So. Okay, any other questions? So. Okay, very good. Okay. But okay, as I said, the Pearson commitment in terms of hiding is better than this one, right? But we got some trade-off. Okay. What if? Okay, let me raise this. So if a committer or anyone knows lambda, then basically the guy can attack this protocol, this very simple protocol. It's one commit, another one verifier, so check the opening. For example, there's an attacker who knows lambda. Then attacker can first of all commit v1, gv1, and with a blending factor R1, right? So we got a commitment like a G V1 plus lambda times R1. And second time, again, the committer will commit another V2. Okay, but using a R star to generate a G V1 V2 plus lambda times R star. But here R star is not a random number actually. So R star equals to V1 plus lambda times R1 minus minus V2 and divided by lambda. Then we put a star, definition of star, into this expression. Then we can say this commitment is equal to this commitment. Okay, it means that we have two different values, but we committed them into same commitment. So this case breaks the second property of the commitment scheme. So binding. So it doesn't satisfy binding property because the prover or committer can commit two different values to a same commitment. Okay. So this is very dangerous. So to prevent the attacking, it means that the G and H should be selected by other third party, trusted third party, or do some trusted ceremony, I think, sometimes. Okay. But in practical, because we don't use the prime field to do this discrete log stuff, we use elliptic curve. For elliptic curves, this trust setup can be done by someone called the transparent setup. Basically, we use some fancy algorithm to both the prover and the verifier, they can agree on something and compute by some predefined constants to get G and H, where the lambda is unknown to both parties. So, but today just we skip that topic, but you should know that. For any cryptographic protocol, it will be very dangerous to introduce bugs, introduce vulnerabilities, which very hard to identify. And you should know that, okay, this step is very dangerous. You should do it in a standard way, or if it is unknown, or please be very cautious and ask for help from experts. All right, so just please remember that the lambda is a kind of in some terminology a toxic waste. So if anybody choose H, then should and he or she should immediately forget lambda or throw it away and keep it secret forever. Okay. Okay. Any questions so far? I can say there's many different commitment schemes like hash. We just use SHA-256 hash or Merkle tree or even for example lattice. On lattice we still have similar commitment constructions. It depends on what cryptographic assumption that you use and according to your application. Right? Okay. Okay, no questions so far? Good. Let's move on to the next topic. Yeah, another things that I missed. Okay, commitment. We have another probably like. Okay, commit. V with G and H as public parameters. G, V, H, R, where R is random. Okay. There's another important property for this Peters commitment. This is called additive homomorphism. Additive homomorphism. So if we have two parties, prover and a verifier, so prover has two secret value, like A and B. So prover, for example, in the first step, prover send G to A, the commitment H, the R1, and in the following step, one step, the prover send GB times HR2 to the verifier. Then the verifier can get the commitment of A plus B very easily. Okay, let me use a capital A equals to the commitment of little a, and capital B equals to the commitment of little b. And then for the verifier just multiply them together. Then the verifier get the G A plus B times H R1 plus R2. Right. So the
The whiteboard a little bit forward because the
light.
reflection of the lights. Yeah.
Okay. Good. Can you help me?
Yeah.
Okay. Put it more. Much better?
Much better.
Good, good. Yeah, thank you very much. Thank you. Okay. Yes. So the commitment has such very good property called additive homomorphism. So if verifier has multiple commitments of respectively A and B, and then the verifier just multiply them together to get A plus B, the commitment of A plus B. Okay. This one is very useful for building efficient protocols.
Question, but the randomness gets skipped because you're just adding two given numbers rather than taking another. There seems to be a problem with the randomness.
Yeah.
In the addition, you use the specific random numbers.
Yeah. Yes.
So
Yes, for sure. For if the protocol uses the homomorphism, then it will be careful to do the security proof to ensure, okay, this randomness is not a fresh randomness, right? It won't be. There is no problem. You should be very careful to prove that step. Yeah, But yes, it is still a commitment to satisfy the definition.
you're using a non-deterministic algorithm to generate the commitment. So
Yeah.
you can never guarantee that you're going to get the same result even with the same input. So it's very confusing what you're achieving with it.
Oh yeah, yes, yes. Sometimes could be dangerous. Yeah, but yeah, we can say the homomorphism can be how it can be used in particle protocol. Then yeah, we're just trying to attack this protocol, see if it's safe. But here is I have to say yes. It's not a commitment like this one, right? The R is a fresh random, right? Yes. Okay. Yeah, let's move on to next topic. Yeah, yes. Okay, next topic is it's called Schnorr ID identification protocol. It's a pretty textbook protocol. So suppose we have two parties, prover and verifier. The prover choose number A from FP as a private key. And the commitment of A use like the public key, the G to A, the public key, pub key. Okay, pub key. Then the prover wants to show verifier that the prover has or owns A, such that the prover can prove the identification of herself. So this is a minimal protocol. Okay, it has only 3 steps. The first step, the prover. Put this. First step, the prover choose a random number. Put random here, random number from FP, and then send capital R equals to G to R. Okay, the first step. And then the second step is the verifier turn. He replies a challenge number, X. X should be random challenge. FP. And then the final step, the prover will send a Z equals to R plus X times A. Send Z here to the verifier. And the verifier will be the final verification step. The verifier will verify something to ensure that the prover has A, knows A. So the verifier will check protocol like this way. G to Z, if it is equals to we use the capital A as the public key. Equals R times A to X. Okay, this is a verification equation for a verifier to check if left equals to right. So if this equation holds, then the protocol, the prover successfully convinced the verifier that prover has A. Okay, right now I stop here for 2 minutes. Maybe you can think that if you can attack this protocol where the prover does not know A, but still the prover can convince the verifier to pass this And also in this protocol, the verifier cannot know what A is. So basically, it's zero knowledge. Yeah. And also it's a sound. Okay, we have the two properties. Sound is zero knowledge. Soundness means that, okay, if the prover who doesn't know A, the prover cannot convince the verifier. It's called soundness. So we will talk that in deep tomorrow. So
maybe you can attack it if you do it twice with the same randomness?
Yes. This is tomorrow's topic.
Okay.
Yes.
I thought you were asking how to attack this.
Yes. But I think the attack protocol is like you have to follow the steps, right? And then the zero knowledge says, okay, the verifier cannot extract the A from the communication. And then we can see because the final step is Z, right? Z is R plus X times A. So we can say that, okay, Z basically we can treat it as the encrypted A, right? Because okay, this one has A, right? And by the way, plus by edited by R, then R is an unknown number to the verifier. Then the verifier cannot get A from Z, right? But if the verifier knows R and if the verifier knows R, then the verifier can easily calculate A, right? But the point here is that R is protected also, right, by using the capital R. So the verifier only knows the commitment of R. But still, the verifier can verify the Z, the third step, Z, exactly satisfy exactly this equation. So the verifier utilize the homomorphism, additive homomorphism to check this equation and lift them into the powers to check this equation, right? So we can unfold the definitions of this equation. Then we can see what happened. So left side of the equation is G to Z. It's like G to R plus X times A. The right side of the equation, the GR times GA X. Then, okay, simple calculation. GR plus A times X. Okay.
Sorry, the prover is giving verifier what? Z and alpha?
The prover gives V the capital R and Z. Yeah. Yeah, capital R and Z, yes. Yeah, 2 more minutes. We will use this protocol again in the following sessions, so because this protocol is pretty minimal. And keep it in your head, it will be very useful for you to understand very complicated Schnorr constructions. Okay. And this protocol also can be converted into a digital signature protocol, which is called the Schnorr signature. Now is deployed in Bitcoin.
Third party could give you X.
Third party, no, verifier. Verifier.
Say a third party gives you X, and that's the message somehow, caching the message.
Oh, yeah, you mean the digital signature?
Yeah. Signature algorithm.
Third party X kind of.
Third party gives me X, and I put some salt in it. That's a verifier. Just puts it in, hash the whole thing, and then when this is a signature scheme already.
I think we can talk about it tomorrow after that we know how to prove it, the security how to prove the security of the protocol. Then we can go back to say if the X is chosen by any third party, so if it is secure or not, or any other condition the X should satisfy.
Oh, X.
Yeah, X, right? X. The challenge number.
X would contain a challenge by the verifier,
Uh-huh.
a message
Oh,
chosen
yeah,
by
yeah.
a third party.
Yeah,
and
seeing.
Hash the whole thing.
Yeah, you're
So
seeing the
nobody can
fair Samir transform.
And then that's a signature of the message that.
Yeah,
the
yes,
party
yes,
gives.
yes, correct. Yeah. Yes, we can use the fair Samir transform to use the random oracle to provide the X. Yes. But here, for simplicity, which is, the X is chosen by verifier. Yeah. So this is still an interactive protocol. I think in the there will be another mentor will sharing something about the fair Samir transform. So I just skip the detail of fair transform here. Yeah. Okay, cool. So. Yes. This protocol, the first step is very important. As the gentleman mentioned, there was many classical vulnerability of either ECDSA's digital signature and a Schnorr protocol. That the first step, the random number cannot be reused. If the random number is reused, there will be. Yeah, the verifier can. Yeah, the verifier can get the private key of prover. Then verifier can impersonate prover. So there was you can Google it in the history that PS4, the PlayStation, got some serious vulnerability that just reuse the first step, the randomness. So for implementation, that you should be very careful about any step of generating randomness. So make sure that it is random first, and it is not reused, and also it is not predictable. Yeah. Okay. So yeah, maybe we can quickly review that vulnerability. If the prover, verifier conduct two instances of this protocol, then by the prover reuse the first step, the randomness, sim randomness, then the verifier can derive the private key of the prover. Okay. So yeah, as you mentioned, it's a very classical attack. Yeah, probably we can just show that how it is done. Okay, I think it's here. So if there's another instance interaction between prover and verifier, okay, the second interaction or a second instance, then the prover and the verifier, the prover first step still send the same commitment R. So the little r is reused. Okay, and the verifier will challenge a different randomness, different challenge number. So let's say x prime, and then the prover, assume prover is honest. The prover will send z prime equals to r plus x prime times a, right? Because p has a, and verifier has g to a. Then verifier got z prime and r. And because the prover reused capital R, then verifier will see that, okay, the first step data that the commitment that prover sends, actually they are equal. Then the verifier can calculate this equation, the two equations. Z equals to R plus x times a from the first instance, and also the z prime from the second instance equals to R plus x prime times a. Now we can easily solve this equation, the two equations. Like we just minus the first equation minus the second equation, then we get z minus z prime equals to x minus x prime times a. Then a will equal to z minus z prime divide x minus x prime. So yeah, we can say that this is very dangerous, right? For if the prover reduces the randomness in the first step, then the protocol is broken easily. Yeah. Okay, any question here?
So now all we know that verifier verifies it. The signer is the right guy. No message. Just you are the right guy. That's all we found out, right? With this.
Mm-hmm.
The only thing that we found out that the prover is the right guy.
Mm-hmm.
Nothing else.
Is the right guy? Yeah. Yes, because we assume prover is honest and verify as the attacker to attack the zero knowledge proof. So attack the zero knowledge property. So if the prover reuses the randomness R, then this protocol is not a zero knowledge.
The whole thing, before this, the Schnorr information, all we find out that the prover is the guy who has the private key, nothing else.
Yeah. Only prover has the private key, yeah. Okay. All right, so and then let's do more things about over the Schnorr protocol. We extend Schnorr protocol to support like a Peterson commitment. So now we just okay. So if we want to protect the privacy better, so we want to use Peterson commitment, then we can extend this protocol to support Peterson commitment. So we have modified some definitions. So yeah, same that prover has a private key, so it's a private, not known to others. And then the public key, we will add a H and R. So the R is generated also by prover. It's a blinding factor. It's also private and very important private. So the prover will have A and R, but A is probably the private key, and R is the blinding factor, blinder. Okay, the R should be kept secret. And then the first step, the Schnorr protocol, the prover will sample two randomness, R and let me use Greek row, use row as the randomness to protect the private key. Here we use R to denote the randomness used in the first step. And R row, the prover will sample two randomness, and the capital R will be G to R and H to R row. And therefore, the same sample only one randomness as challenge number. But in the third step, the prover has sent two value, R row plus X. The row. Yes. And what about the verification equation to be like G to Z times H to Z row. So yeah, this is a Schnorr protocol extended with Peterson commitment. This protocol is more privacy protection. It satisfies perfect zero knowledge property. Yeah, we will prove the properties tomorrow. So okay, I stop here, and for a couple of minutes, and it's time for a question. So. Sorry?
How many lectures do you have together?
I don't know. It was this week, and we still have two more lectures. Tomorrow, proof by simulation. We use simulation paradigm to prove the soundness and zero knowledge properties of this protocol. And also on Friday, probably we will extend this protocol further to prove some support some simple application like data storage, something like that, yeah. And file exchange, more application oriented on Friday. And tomorrow kind of more theoretic to prove the security. Yeah. And next week probably have planned that introduce the Planck based on the knowledge we the basic concept in the first week. Yeah. Yeah. Any other question? Yeah. Okay. So.
Thanks.
I'm really a beginner in this stuff.
Okay.
So
Okay.
I don't know much about other protocols. Can
Yeah.
you give us like an overview of like what makes this protocol special in comparison with other ones? And if you think this will be used a lot and why?
Okay. Because first of all, this protocol is only 3 steps. It belongs to a family called Sigma protocol, which was researched intensively during 90s. I think it's relatively easy to get the intuition by watching and understanding this simple protocol. But for modern Schnorr, it could be very complex. If we want to, for example, improve the efficiency of prover, either improve the efficiency of prover or compress the proof size, because proof size is very important, right? So we have to do more work based on this Schnorr protocol. So basically, we can extend the Schnorr protocol all the way to, for example, to bulletproof, and with the other modern Schnorrs using this as pieces, building blocks. Okay, so it is very simple. So, for example, the group 16 or Planck or Stock, it might much more complicated. So it will be much harder to find any security issue. So even you follow the spec, but you don't know, you have to know that why this step is important. Just we get started from a very simple example to get more intuition. For example, why we put a randomness here? Why the verifier can check this way? Is this complete or not? For example, yes. Did I answer your question? Okay. Okay.
So just double check, like the active homomorphism is a property of Peterson.
Oh, okay. Peterson commitment satisfies additive homomorphism, so it has this property. But other commitment schemes like Merkle tree, it hasn't this property. So for some build a larger complicated snark system like a folding scheme, the Peterson commitment will be much easier to put it into a circuit instead of, if you want to use the Merkle tree, it will be costly.
Nice.
Yes.
Yeah. In the third step here, we use the active homomorphism, right?
Yeah, for sure.
Okay, and the R in the first step is the commitment, right?
Yes.
And then we use these R also in the third step to compare. For the verification.
Yes, in the verification step, yes.
Okay.
Yes.
Okay.
Yes.
Just to double check.
Okay. Thank you. So, any other questions? Also, I want more feedback. So I know what you are curious about or what you want to learn, that I can add more stuff if you are interested in some modern Zig-Snarks. Because this one is pretty classical. It's a textbook example. So you can Google it or refer to serious cryptography textbook, you'll find this one, and more explanation and more security proof. Yes. But here I just quickly go through this example give you more intuition that how protocol works. Yeah. I think, yeah. Okay, thank you for listening. Yeah, see you tomorrow. Oh, sorry.